Okay, so we are solving the problem of the finite square well. So let's draw it here. So the finite square well is 0 up to minus a. There it becomes some value minus v naught. And then at a, it becomes 0 again. Okay? And we already solved the case where the energy was negative. This case of the energy negative is the one that gave us the bound states. So this is already done. Now what we are going to do is we are going to choose the energy positive. So the energy positive means now that we have scattering. So that's the case of scattering states. Okay, so before going to the math of this problem, let's think a little bit about it. Let's try to examine this problem. So again, we are going to separate the problem in three regions, region 1, 2, and 3. And let's look at each one of these regions. So in region 1, what we have, the energy is larger than the potential. So even classically, we would have no problem having this particle there, so classically allowed. Region 2 is the same story. Né? Again, the energy is larger than the potential, classically allowed. And finally, the region 3, same story again, classically allowed. So I think we can even copy this and put it there. All right. So if it is classically allowed, before we go into the math, what do we expect? We expect sinusoidal functions. We expect, so let's write what we would expect. We expect sine or cosine or equivalent exponential of I kx, exponential of minus I kx. As we already said many times, this solution, this combination of sine and cosine can be written equivalently in terms of the exponential. Now, there is a problem that we solved that shows that these two things are equivalent. Well, when do we prefer one over the other? It's convenient, both are correct, but it's convenient to use this one when we need to think whether the motion is to the right or to the left, whether the wave is moving to the right or the wave is moving to the left. So this is more convenient. When we are in bound regions of space, well, then this one is more convenient. Okay, so the one that I'm marking in orange is more convenient where we have this possibility of moving to plus infinity or minus infinity. All right. Okay, so let's keep this in mind. This is the kind of solutions that we expect for the three regions. And now let's really go through the math. Okay, so let's start with region 1. In region 1, the potential is 0. So when we write Schrödinger's equation, the potential is 0, so we go straight energy side. Okay, and then we play a little bit with this equation, pass the constants to the right, and here we are. Now, we are going to incorporate all of these constants that we see there, including the energy, in a single symbol squared. The energy, and I'm going to mark it here, the energy, as we already said, is positive. So to have a quantity squared, I am not going to pick the minus sign. I keep the minus sign out, and I'll call this k squared. So my equation now is minus k squared psi equal to minus k squared psi. And what is the solution for that? What are the functions that I derive twice and I get this minus sign? A sine, a cosine, or an exponential with I. Now, this region that we are talking about now is this region here, where, yes, the motion could have started in minus infinity. So in this sort of region, it's more convenient to write the solution in terms of exponential with I. And so I'm going to write this solution here as a constant exponential plus I kx and a constant exponential minus I kx. Very good. Now let's move to our region number 2. Everything is very similar, except that in region 2, we do have the potential. No, it's not 0. It has a value here, minus V naught. So let's write this in our equation. And so now do keep the potential. I'm already going to take into account that it's negative. So I'm putting this minus sign here because I'm already taking into account that it's negative. So this V naught that you're seeing there now is just the absolute value. And because I already took the sign into account and the energy. Okay, so again, we rearrange this whole thing. But maybe we can do it in 2 steps to make it very clear that first I'm going to pass the potential to the right side. Plus V naught. So everything that we have there is positive. And this V is positive, and this V naught is also positive because, as we said, we already took its sign into account. So this symbol here is indicating a positive number. Okay, all right. And then now I'm going to rearrange. Now I'm going to pass the constants to the other side. All right. So again, we are going to put all these symbols, and I forgot to put the sign. So I'm going to put all these symbols into a constant squared. And then, since we already said that this is positive, I'm not going to take the sign into my constant because my constant is squared, so it has to be positive. And now to distinguish from the K that we used before, no, the K only had energy. I'm going to give it a different name because here I have energy and V naught. So I'm going to call this now L square. Yeah? All right, so now we have our equation with the minus sign, and we know that if there is a minus sign, it has to be a sine, a cosine, an exponential with I, exponential either with plus I or minus I. But look, this region 2 is this region between minus A and A. So here, it's convenient to write in terms of sine and cosine. And that's what we are going to do. So the solution is going to be C sine of Lx plus D cosine of Lx. Very good. And now we go to the last region, region 3. And region 3 mathematically is equivalent to region 1. And region 3 is this one where the potential is 0 and we can go to infinity. So we can just copy what we had here because everything is going to be very similar. Yeah? So it's the same scenario, and so I'm just going to rewrite what we have here. Yeah? So This is the equation that we are trying to solve with a minus sign in front. So we know the solution is sine or cosine exponential with I. In this scenario, because we can go to plus infinity, it's convenient to write in terms of I, because I can identify which piece is moving to the right, which piece of this wave function is moving to the right, and which one is moving to the left. Okay, so this is the complete mathematical solution. Okay, so let's mark all the equations that, all the solutions that we found. We have this for region 1, this for region 2. So I'm going to name this psi 1, psi 2, and this is the solution for region 3. I'll call it psi 3. All right, now let's think a little bit. When we start these problems, when we start the motion, we usually think about the particles being thrown from one direction, being fired from one direction. You can choose either to throw it from minus infinity or from plus infinity. Usually, what is done is we assume that we fire these particles from minus infinity. What that means then, that this part of our solution, the A with the plus ikx, once we add to this story the time dependence, this will give us, as we already discussed, this will give us the part of the wave that is moving to the right. So that part with the A indicates the one that is moving to the right. Now, when it finds this perturbation here at minus A where the potential changes, part of it gets reflected. And I'll call this part, the part that gets reflected is the B part, now with the minus ikx. Now, if I add there the part that depends on time, we'll see that this is the piece of the wave moving to the left, getting reflected to the left. Okay, so let me repeat in case I said a new word wrong. The part with A indicates the one that is moving to the right because we have plus ikx. The part with B indicates the wave moving to the left because we have the minus ikx. Okay, then we go through the part of the wave goes through region 2. In point A also gets reflected. So we have inside here the sinusoidal waves with the C and D. And when the wave reaches this point plus A, part of it gets transmitted. And what is the piece that gets transmitted? The one with the F, because we have plus ikx. Again, once we introduce the time dependence here, we'll see that this is the part of the wave moving to the right, the one that has the plus ikx. Right. And then it's going, and then it's going, and then it's going. There is nothing in front of us, ahead of us, to reflect these particles. Okay? So if there is nothing to get reflected once we enter that region 3, that means this part, this G, even though mathematically is correct, is not part of our solution. Okay, so the G doesn't exist. All right, so this is the solutions that we have for the 3 regions. How do we move from here? Well, we have to play with boundary conditions. And we have boundary conditions at position minus A and at position A. This problem now is different from the case of the bounded states in the finite square. Well, there was some symmetry, so we could split the solutions either just sine or just cosine. Now we cannot because we have this asymmetry in this region 3. Yeah? It's an intrinsically asymmetric problem. So we really have to play with all boundary conditions in point minus A So the boundary conditions here at minus a and the boundary condition at plus a. All right, so it's tedious, but let's just go for it. So at minus a is when these two functions need to be stated. Is where we have this meeting point. So let's write from minus a, we need that the function 1 at minus a be equal to the function 2 at minus a. All right. In addition to that, we need that the derivative at minus a be equal to the derivative of psi 2 at minus a. All right, that's what we need. Now let's go step by step. So I'm going to erase this part and first write that the function has to be. Okay, so if I write that the function has to be equal, I put a exponential ik, now minus a, so I'm going to put minus a. And then plus b exponential minus ik with minus a, so this becomes plus, equal to, then we have sine of L minus a. Now, the sine of minus theta is minus the sine of theta. Okay, so that's what I'm writing here. Why is that? Think about the sine. The sine of theta is this projection here, positive. But the sine of minus theta is this projection here, which is negative. Okay, so that's what the property of sines that we are using. Then we go for the cosine. So plus d cosine L minus a. Well, cosine of minus theta is equal to cosine of theta. So we don't need that minus sign. We can just put a. Okay? And what I'm using is the property of the cosine. So the cosine of theta is this projection here, which is plus. And if I look at cosine of minus theta, it's the same projection. It's also here, it's also plus, okay? All right, so this is done. Now comes the derivative. Be very careful because I often see people losing track of what is the derivative that you have to do. You have to do the derivative of this function. This is the function with x. This is the function with the variable, not this one. I often see this mistake. Okay, we are going to do the derivative of this function, the derivative of the wave function. So the derivative of that is ik and then minus ik. Okay? So first you do that, and then you substitute by the value of that variable at minus a. Same thing here. We are going to do this derivative of the function in x, and that gives us L sine or cosine of Lx. Then the derivative of the cosine gives us minus L and the sine. Okay, so now I'm going to substitute what we obtained here. I'm going to substitute the x with the minus a and the x with the minus a. So be very careful with this. Don't make this silly mistake. Okay, so there we go. Then we have ik exponential of ik minus a minus b exponential minus ik with minus a. This becomes plus. Very good. And this is equal to, now I go to the derivative, and this result that we have here. And then we have L C cosine of L minus A is just the cosine of A, no problem. And then minus D sine of L, now minus A here. Sine of minus theta is minus sine of theta, right? So this minus here we can remove, and this becomes plus. So, very good. And so what we did was to write the derivative of the function, the psi1 at minus a equal to the derivative of function 2 at minus a. Very good. So now we are done. Okay. So this, we now have these two equations. And so these two equations that we obtain from this point minus a. Now we have to do the same exercise, playing with the position plus a. All right, so that's the same story. Now you know where you have to do the derivative to avoid mistakes. So we are going to do now this part with the sign equal to this part. So we are running out of space here, but we have psi 2 will have at plus a will have to be equal to psi 3 at plus a. All right, so that will be sine of L a plus d cosine of L a equal to f exponential of I k a. So this one is a little easier because we don't need to worry too much about the signs. No? So a, and a. All right, and then the derivative. Okay, so careful with the derivative. We are going to do the derivative of this function. We already did it. I'll do it again. L, and here we have the cosine, minus, and here we have the sine. Okay, so with this solution, I'm now going to put at position A. So we have L C cosine of L A minus D sine of L A. And again, now the derivative of this part, the derivative of this part is simple. Is just F, well, IK, F, and the exponential. So here we have IK, F, exponential plus IK, A. All right, so it became a bit squeezed there, but now we have all four equations, this one and this one as well. Okay, so now what is it that we have to do? This part is a bit tedious because we have these four equations, and the purpose now is to manipulate these equations and get rid of the C and D. Okay, the C's and D's everywhere, because what we want to do is we want to find a way to write F as a function of A only. Why? Because the transmission coefficient is this ratio. And we want to write B as a function of A only. Why? Because the reflection coefficient is this ratio. Okay, so that's why we have to manipulate all of these equations to try to get rid of C's and D's along the process. This is the subject of the problem 2.32. I'm just going to discuss with you the solutions. Okay, so once you find this relationship between F and A only, you are able to get the transmission coefficient, as we said. And what is going to be this transmission coefficient? I'm going to copy this from your book, and this is the equation 2.172. And it's a long equation. One plus, and then you will see all these constants showing up, the V naught square, the energy. And very important, there is a sign in this story that gives a very interesting result. Because what do we usually would expect in this kind of problem? So this is the equation. What we usually would expect in this kind of problems? Well, we have our potential energy. As the energy goes on increasing, as the energy gets larger and larger with respect to this potential, what we would expect if we would make a plot of this transmission coefficient as a function of this energy, we expect it to go growing until this energy is so large that the transmission is 100% transmitted. But that's not what we see. And that's the interesting thing, because it is growing with energy, but there are some very special points where this sign becomes zero. When will this sign become zero? When what we have inside here is a pi or 2 pi, any product of pi, any integer multiplied by pi. So this sine function becomes zero when what we have inside there, 2a h bar, the square root of 2m e plus v naught, all that, when all that is equal to n pi, when this n is an integer, that thing goes to zero. Well, what is special about that? If the sign disappears, you see that the transmission coefficient goes to 1. So what we actually have in this transmission coefficient, this was seen experimentally, is that instead of this smooth growth, we have some peaks along the way when we go to 1. Now, when the sign goes to 0 and the transmission goes to 1. So these are very special points. And this happens when this is satisfied. What does it mean, this being satisfied? Is a special value of the energy. Some special values of the energy will get this peak of transmission. And this happens when I'm going to square all that to isolate the energy. We have h bar square, n square, pi square over 2a square. And you see that what we have is the energy being equal to n square, pi square, h bar square over 2m 2a square, which is, again, the recurrent result, no? The energy of the infinite square well. So these are special points where the transmission is perfect, even though the energy is not sufficiently large. Okay, so this is the end of this discussion.